All right, so buckle up, everyone, because today we're taking a deep dive into a paper that's really challenging some fundamental assumptions about how energy moves through the universe.
Oh, yeah, this one's a doozy.
It's called From Straight Beams to Curved Paths, a unified perspective on energy fields and space-time. And, well, it's basically suggesting that maybe we need to rethink this whole idea that energy travels in straight lines.
Yeah, that's putting it lightly.
So to help us break down this pretty complex topic, we have an expert in both quantum field theory and general relativity.
Hi there.
So let's jump right in. I mean, the title itself kind of gives us a clue, but what's the core idea here that's got everyone buzzing?
Well, basically, it boils down to this long-standing tension between quantum field theory, or QFT as we call it, and general relativity, GR.
Right, two of the biggest pillars of modern physics.
Exactly. And they don't always see eye to eye. I mean, QFT usually assumes a flat space-time background where energy just zips along in straight lines, nice and neat.
Makes sense in a simplified model of the universe.
Right. But then you've got GR, which tells us that mass and energy warp space-time itself, meaning energy's path, should actually be curved.
So it's like trying to draw a straight line on a crumpled piece of paper. It just doesn't quite work.
A perfect analogy. And that's where this paper comes in, proposing we ditch those straight beams and instead picture energy moving in these expanding spherical or elliptical wavefronts.
Okay, so instead of like a laser beam shooting through space, we're talking about something more like ripples spreading out from a pebble dropped in a pond.
Exactly. But here's the twist. Imagine that pond surface is actually curved, representing the curvature of space-time.
So those ripples are spreading outwards, but they're also following the contours of that curved surface.
Precisely. It's a much more dynamic and, well, realistic picture of how energy might be moving through the universe.
Okay, I'm starting to get the picture here.
Mm-hmm.
But before we get too deep into the weeds, I think it's worth asking, is the whole straight line energy propagation idea really that much of a problem? I mean, it seems to work pretty well in a lot of cases.
Yeah, you're right. It's a good simplification for a lot of everyday situations, especially when you're dealing with smaller scales or weak gravitational fields, like throwing a ball or, even sending a radio signal across town.
Right. We don't need to account for the curvature of space-time to get those things to work.
Exactly. But when you start zooming out to cosmic scales or considering things like black holes and neutron stars where gravity is super strong, well, those straight lines just don't cut it anymore.
So it's not just about replacing straight lines with curves for the sake of it. It's about acknowledging that the very fabric of space-time is this dynamic, warped thing.
Precisely. And to really capture that, you need a more sophisticated mathematical framework. And that's what this paper proposes.
Okay, so let's talk math for a minute. How does this new framework actually work? What are the key ingredients?
Well, one of the key players here is something called spherical harmonics.
Oh boy, those sound fun.
They're actually pretty cool. They basically provide a mathematical language to describe the shape and evolution of these expanding wavefronts as they move through curved space-time.
So it's like going from a flat map to a globe. You're getting a more accurate representation of the terrain.
Exactly. And what's really exciting is that this paper doesn't just stop at describing these wavefronts. It actually goes a step further and composes a specific equation that combines elements from both QFT and GR.
So they're trying to find this common language, this bridge between these two seemingly disparate theories.
That's the goal. And this equation they propose, it combines the wave function from QFT, which describes the quantum state of a particle, with the metric tensor from GR, which describes the geometry of spacetime.
Wow, so it's like they're taking these two puzzle pieces from different puzzles and finding a way to fit them together.
That's a great way to put it. And what's even more remarkable is that this seemingly simple change in perspective from straight beams to curved wavefronts, it has some pretty profound implications for how we understand a whole bunch of phenomena.
Okay, now you got my attention. Like, what kind of phenomena are we talking about?
Oh, everything from redshift to gravitational lensing, even wave-particle duality. This isn't just some cosmetic change to our equations. It's a fundamental shift in how we think about energy and its relationship to space-time.
This is where things start to get really interesting. So let's start unpacking these implications one by one. First up, redshift. How does this curved wavefront model change our understanding of why light from distant galaxies appears shifted towards the red end of the spectrum?
Well, the traditional explanation of redshift relies solely on the stretching of space itself as the universe expands, which is definitely a part of it. But this new model adds another layer. It says that as the wavefront is propagating through this curved spacetime, its shape is also changing, which leads to an additional stretching effect.
So it's not just space expanding, but the wave itself is also evolving in a way that contributes to the redshift we observe.
You got it. It's like, imagine you're stretching a rubber band, and at the same time, you're also kind of pulling it taut around a curved surface. You're getting this double whammy of stretching that can really amplify the effect.
Okay, that's a great visual. So it's not just about the distance between galaxies increasing. It's about the very fabric of space-time affecting the light itself as it travels.
Exactly. And the implications don't stop there. This model also offers a new way to think about gravitational lensing.
Ah, yes, the phenomenon where massive objects bend the path of light like a cosmic magnifying glass.
Right. And instead of just thinking about those neat, perfectly bent light rays we see in diagrams, this model says that the entire wavefront is being distorted as it passes by these massive objects.
So instead of just a single point of light being bent, we're talking about a whole wave being warped.
Precisely. And the paper suggests that this distortion due to curved spacetime could actually lead to subtle shifts in the polarization of the lensed light.
So we're not just talking about a thought experiment here. We're talking about potentially observable effects.
Exactly. And that's one of the things that makes this research so exciting. It's not just theoretical, it's giving us new ways to test our understanding of the universe.
This is definitely getting my brain fired up.
Yeah.
But before we get too carried away with all the mind-blowing implications, let's bring things back down to Earth for a second. What are some of the practical implications of this model? Like, how could it change our understanding of the universe in a concrete way?
Well, one area where it could have a big impact is in our understanding of redshift.
Okay, we talked about that a bit already, but how could it actually change things in a practical sense?
Well, remember, the traditional explanation of redshift is that it's caused by the stretching of light waves due to the expansion of the universe, right? But this model suggests that redshift isn't just about the stretching of space itself. It's also about how those wavefronts themselves are evolving and stretching as they travel through curved spacetime. Which means that the redshift we observe might not be a completely accurate measure of distance.
Oh, so it's like we've been using redshift as this cosmic ruler to measure the distances to faraway galaxies. But what if our ruler is slightly warped?
That's a good way to put it. And if that's the case, it could have a huge impact on our understanding of the universe's expansion rate and its overall history.
Okay, now that's what I call a game changer. So it's not just about tweaking existing theories, it's about potentially rewriting our entire cosmic narrative.
Exactly. And that's why this research is so compelling. It's not just about adding another layer of complexity. It's about finding a more elegant and unified way to describe the universe, a way that takes into account the fundamental interconnectedness of energy, space-time, and everything in between.
Well, I'm definitely hooked. This curved wavefront idea has the potential to turn our understanding of the universe on its head. And I, for one, can't wait to see what evidence emerges in the years to come. But hey, that's a discussion for another time.
I'd say so.
We've covered a lot of ground today, and I think it's time to give our brains a little break.
Yeah.
But don't worry, we'll be back soon to delve even deeper into the mind-blowing implications of this curved universe.
Looking forward to it.